Okay, today I want to talk about molecules. Let's start. So we first understand the quantum mechanics, and then we applied it to the simplest realistic system, which was the hydrogen atom, which was like a single ion, which was fixed, and there was like an electron in the orbit. And then we generalized it to many electron case. And in the many electron case, we only use two principles: Pauli principle, of course, energy minimization, and also screening. And now the next step is to consider more increase the complexity and consider talking about molecules. And for this, we have to talk about so-called molecular bonds. In nature, we generally see not single atoms, right? We almost never see single atoms other than the inert gases. Typically, atoms come together and form molecules. And here we first want to understand why molecules form. And for this, we have to consider there are many molecules, but we have to consider two basic mechanisms. Let me first outline what they are, and then we are going to try to understand the mechanism behind these using our understanding of quantum mechanics. The first is covalent bond. And in which the electron is basically shared between the members of the molecule. So, in this one or more electrons are shared between atoms in molecule. An example is, for example, hydrogen, and you have like two hydrogen atoms. Like there's like one like plus charge, and there's like an electron cloud, and there's another hydrogen atom the same way. And when you bring them together, what happens is like you have these charges, and then if you want, like you have like this shared electron cloud. So both of these electrons are shared for the hydrogen atom, and you can see there's like an increased probability to find the electron in between the ions. Increase probability in between ions. Of course, electrons increase probability. And in this case, for example, the binding energy of two hydrogen atoms, binding energy, for example, which we are going to talk quite at length today, is minus 4.5 eV. And you can compare this with like always our like basic energy scale is like kind of like 13.6 eV, which is the binding energy of electron in the hydrogenic atom. So this is the first one. The second one is ionic bond. Ionic bond. In this case, one or more electrons are transferred from one atom in molecule to other. Another. Again, the most stereotypical example is sodium chloride, which is table salt. And in this case, sodium is, okay, we are going to talk today, but like in brief, what matters is the outer shell electrons. What is happening in the core actually is irrelevant. We probably have a sense of this, but we are going to talk about it more. In the sodium case, we have like plus 11 protons in the nucleus, and if you want, there's like, I'm going to smash all of them to like this, minus 11 outside, and you combine it with chloride, which is plus 17 in the middle, and minus 17 in the cloud. And when you combine the molecule, what you do is you take one electron from here, like this is going to have minus 10, and you are going to have, this is going to have minus 18. As a result, this blob is going to be like net plus charge, right? Plus 11 minus 10 is going to be plus E, and this blob is going to have minus 18 plus 17 is minus E. Because these two objects are charged, they are going to electrostatically pull each other, and they are going to stay together. And that's the ionic bond. And one important difference between ionic bond and covalent bond is like, typically we can see like a isolated H2, for example, but not isolated sodium chloride. Sodium chloride generally comes in like a crystal structure where equal amounts of sodium is bound to equal amounts of chloride. Okay, any questions or comments?
The bond strength equal to column cloud. These two positive electron charges.
For this one, yes, but like in more general terms, yeah. In more general, like for a sodium chloride, it looks like it is just a coulomb, but there is also like an electron, right? And typically in real life, what we have is not purely ionic or purely covalent. We have something in between, right? Some of them are more ionic, some of them are more covalent. And what happens is like, yes, you have to take both the Coulomb interaction between the ions, but also there's like electron, right? And electron has like some quantum mechanical wave, and the configuration of this quantum mechanical wave is going to modify this pure Coulomb interaction, which we are going to try to answer today.
But you don't mean by isolated H2 and not isolated.
So what I mean is like in nature you can see like, right, if you look at the hydrogen gas, it's like these like individual gases, and they are kind of far away from each other. Of course there's like some, if you bump two molecules into each other, they are going to, but what happens in the sodium chloride is like you have to put all of them in a crystal structure like this, right? And some of them, like this one is going to be, for example, sodium, this one is going to be chloride, and so on. So this entire crystal structure is bound together, not just one bond. Any questions or comments? And to understand these things in more detail, we have to look at the simplest possible molecule, right? Simplest possible atom is hydrogen atom, right? There's only one electron, and it's very simple. Although it's like complicated wave functions, it is simple, it's exactly solvable. And for the molecules, the simplest possible molecule is H2 plus molecule. And in H2 plus there are like two ions, one from each hydrogen, but only one electron. This is one, and only one electron. And the question is, how should we allocate the single electron between these two ions? That's the problem. So we can kind of think about, like, let's consider the potential. Let me just draw the potential over the ions. So let this be the distance, and let's here, let me erase this. Let this be U of R, right? And U of R is Coulomb interaction, and I'm only considering potential for electron, right? There's also potential energy between the ions, which are going to include at the end, but for the moment, suppose these two ions are given to us, they are fixed, and we want to draw the potential felt by a single electron. What will happen is something like that. So, right, this is like Coulomb as it comes to here, and another Coulomb here, and like that, right? So these are each E squared over R, but as R goes to the location of ion, it's going to blow up. And because ion nucleus is positive and electron is negative, there will be a minus here, that's why it's going to minus infinity. Is that clear? So we can model this. Okay, let me pull this aside. We can model this. For example, we can think about, rather than this complicated shape, we can think about double well potential, right? Right, finite double well. And what we know from for example, tunneling studies, yes, there is like an amplitude to find the electron here or there, but because of tunneling, there's also finite probability to find the electron in between the two wells, right? So this is finite probability in, let me say, due to tunneling, which is purely quantum effect. And for tunneling to take effect, the distance between these two wells should be close so that there can be some overlap between the wave functions. If these two wells are separated infinitely far apart, there will be no overlap, and we can forget about this finite probability. Whereas if they are very close, there will be a finite probability, and that may be responsible for bonding.
Where are electrons in that wall?
Inside the wall or here?
Yes, I asked.
Both, right? We cannot say electron is here or there.
Protons.
So proton is right in the middle, right? If you want, this is the real physical potential, but we can approximate it with these two double wells, and then in the double well case, right? I think there will be some probability amplitude here, there will be some probability amplitude here, but not only that, there will be also, even though classically forbidden, there will be some probability amplitude in between. So that's what we are trying to argue. So before doing this more carefully, there is an uncertainty argument, which is much simpler. So uncertainty. Yes. Which area in the diagram corresponds to?
The wall.
The wall is here, right? This one. So we are considering some energy level like this for it to be bound, because if it was here, the electron would be unbound. And from our quantum mechanics studies, we said that there's a bound state if energy is below the potential energy. And for this energy, the wall is going to be here, right? In principle, there cannot be, classically, there cannot be any electron here, but we know quantum mechanically it is possible because of these decaying solutions.
So how do you relate that to the diagram, left diagram?
This one?
Yeah.
They are identical. Here, for example, I'm thinking about an energy here, and if the energy is here, there's I don't know, there will be a probability here, there will be a probability there. And in principle, because of this energy, this is classical turning points, right? But because of quantum tunneling, there will be also some amplitudes inside. And these amplitudes inside correspond to electron being in the middle of two ions, or electron being shared by two ions. So in the uncertainty picture, if you remember, smaller delta x, then larger delta p, right? Because delta x delta P is bigger than or equal to h bar over 2. But bigger delta P, of course, P and delta P are different. We are making like arguments. We are trying to get the most information with the minimal work. And for this, we have to relate delta P to P. Right? We say if delta P is large, that's a good reason for us to believe that P is large. Right? And if P is large, then kinetic energy is large. Right? And the argument is by just delocalizing the electron, right? Rather than electron being here or there, I can delocalize. An electron can hop from here and back and forth. By doing this hopping back and forth, it can increase delta x, but increase delta x is going to be decrease delta p, and decrease delta p is going to be decrease energy. So electron can decrease its energy by hopping between these two wells. A lot of words, but hopefully that's clear, right? Then kinetic energy is large. Then electron can minimize energy using both boxes at once. Good. Any questions? But of course, we need to think about, right? We now do things the proper way, and the proper way is just go there, find the wave function, solve the Schrödinger equation, and find all observables. That's how we do things at the moment. And for this, we have to think about wave function. As a function of separation. So we are going to consider what happens to wave function as we tune the distance between the ions, and what happens to the corresponding energy. So let's first consider two limits. Consider two limits. Let's say delta R is the distance between two nuclei, R1 minus R2. Like this is, so this is, if you want, delta R. And when delta R is much larger than Bohr radius, let me call it E Bohr, which is something like 0.5 angstrom, we can consider like two independent wave functions, right? There's like, here's one ion, here's the other ion. So this is R1, this is R2, this is the R, and one electron is going to have like, this is the 1s, right? We know very well how it decays. It's like just e to the minus r over a Bohr. There's another one here. So let's call this psi 1, let's call this psi 2. So these are like 1s orbital of hydrogen atom, which we know well. In the opposite limit, if delta R is equal to 0, right? We smash these two nuclei together. That means there's only one charge, but the magnitude of charge is twice the magnitude of charge in the hydrogen atom. In that case, if you want, let me draw it here. Yeah, like something here. And because of this charge, the Bohr radius is going to decrease because there's more charge, right? It's going to squeeze electron a little bit more, and energy is going to also modify, right? So let's draw it like this. So this is, again, what do I call it? This is, let me not call it anything. This is 1s orbital of, this one was hydrogen, this one is going to be what? Which atom? With two ions in the nucleus. Which atom do we know? Helium. The one is orbital of helium atom. Which is like, so let me just also write. Same as this one, but smaller Bohr radius. Because the charge is more. So these are the two limits, but in between, so this is one limit, this is another limit. In the intermediate regime, so the wave function should be some combination of these two, right? Intermediate regime delta R is comparable to a Bohr. So we have to use both psi1 and psi2. And there is only one principle we know. In this case, if this is the center of coordinate system, right? We studied this before. You can go to lecture notes and study that part one more time. We are forced to have either symmetric or anti-symmetric wave functions, right? Because the space has this symmetry, Schrödinger equation is going to have this symmetry, so we have to have wave functions which obey either symmetry or anti-symmetry. And two options, when in the intermediate regime, when delta is comparable to a Bohr, we have two options. We can either have, okay, let me again write this. And we can either combine them in a symmetric way, like this, right? So this is again, this is R1, this is R2, these are psi wave functions, and this blue line here is psi1 plus psi2. And symmetry means if you invert with respect to a mirror put in between the atoms, it should return to itself. And the other option is, I can also do that, right? So, like something like that. I cannot draw something like that. Something like that. And this one is going to be psi1 minus psi2. And if you invert with respect to a mirror in between the molecules, this new wave function is going to minus of itself. Is that clear?
When you said when we smash the positive charges, under what condition does all this happen? When do they smash or combine?
Of course, we cannot smash, we are imagining, right? You mean here, right? We are thinking about two ions slowly approaching. When the two ions are at the same location, that means what? That means I have like a single charge at one point, but the magnitude of charge is 2e rather than e. And that is, I know of helium atom, and I know from the solution of helium atom, this should be the wave function. But now we are looking at the intermediate state where these charges are separated, but electron has to choose, right? Electron has to choose one ion or another. But based on this, there is like two options, symmetric or anti-symmetric wave functions. Now we have to determine which one is the smaller energy. Good. And now question is, okay, let me call this one symmetric is equal to this, and this is psi anti-symmetric is equal to this. And the question is, which wave function has smaller energy, psi symmetric or psi anti-symmetric? Any suggestions? Anti-symmetric is smaller energy. Why?
They somehow make a form destructive.
Mhm. Any other suggestions? Anybody want to say symmetric? Yes, why? Mm-hmm. Yeah, so to determine this, we need to consider the limits we just outlined. So as delta R goes to 0, psi symmetric is going to go to psi 1s of helium atom, right? That's what we know. And psi anti-symmetric, you can see there's like a node in psi anti-symmetric. And as you continuously decrease the distance between ions, you cannot do anything about the node. Node is going to be there, and the wave function with the node, when the delta R is 0, delta A goes to psi, if you want 1s, 2s, 2p of helium atom, right? One is going to go to s orbital, which is going to be symmetric. The other one is going to go to p orbital, which is anti-symmetric. Is that clear? And which one has the higher energy in this delta R goes to 0 limits? Right? S is smaller and P is higher, right? Or then let me call it ES is smaller than EA in delta R goes to 0 limit. But now we can kind of consider like slowly increasing delta R from 0. As we slowly increase delta R, ES is still going to be smaller than EA, but maybe in limit delta R goes to infinity, ES is going to approach to EA. Is that clear? But as in the intermediate regime, we have to pick up the symmetric component because of this argument. So then the argument is psi A, which is equal to psi 1 plus psi 2, has smaller energy. And that means more probability in between ions. And if there are like more electron in between the ions, that means like a bonding, right? By putting like a glue kind of like in between two ions, which is the electron, I can hold these two ions together. So now we can consider but there is also like a Coulomb interaction between the ions. So we also have Coulomb interaction between two protons, two ions. So now let's also put that in. So far we only considered the energy of the electron, but now putting the energy due to two ions. And let me write it, V ion-ion interaction is a function of delta R is going to be 1 over 4 pi epsilon naught E squared over delta R, right? This is simple Coulomb. The sign is positive, whereas in the electron and ion case, it was negative, because electron is positive charge and ion is negative charge. In the case of two ions, they are positive, so this V of R is going to, okay, let's plot these two. So let's say this is R, so this is energy, so this is energy, this is delta R. So this V ion-ion, let me draw it like this, so it's going to be something like that. Right, this is V ion-ion. Let me call this R. It's kind of awkward to write delta R everywhere, so this is V of R. And so now let's also determine the electron-electron energy. So E electron is equal to what? As R goes to infinity, what is the electron energy, right? So what is the 1s electron? When they are like far separated, electron can be here or there, and we know there is only one electron, and its energy is what? If I have, like, suppose for like if they are infinitely separated, I can just forget about one of them, right? What is the electron energy for like 1s orbital? 13.6, right? And if it is here or there, doesn't matter, right? If it's here, it's 13.6. It's here, 13.6. So then there's like some region here. Okay. Let me call this. So this is minus 13.6 eV, and here we start from here, right? And when the separation between, so this is E electron is equal to minus 13.6 eV as R goes to infinity, and E electron is equal to as R goes to 0. Now this limit, right, this one, when the separation between ion is 0, we have the 1s orbital of the helium atom, and we need to calculate the energy of 1s orbital of helium atom. What is that?
Helium atom with 2 electrons?
Yes, with one electron, but 2 ions, 2 protons in the center. Z, right? So it is minus Z squared times 13.6, right? And Z is 2, and that's going to give us, what is it? Minus 54.4 eV, which is, okay, let's pull this down a little bit. So this, okay, this is not to scale, but it's going to be somewhere here, right? Minus 54.4. Okay, let me just. Then, like, I should, right, as I go from here to here, I should continuously go like that. I should connect this end to this end. And now you can imagine how you want to connect, but like the reasonable thing is to smoothly connect one curve to another, right? Something like that. So this is, the blue is ion energy, so the red is electron energy. Electron. And now I need to calculate the total energy. Actually, let me use a different color for this. So maybe this one. Now total energy is what? Total energy is E total is equal to E electron plus V ion as a function of R. And if you sum this, right, when it is, okay, now I can use red. When they are far separated, it's going to be like this. When R is equal to 0, infinity always wins, right? No matter what you subtract from infinity, it's going to be infinity. So it's going to come from here. And presumably there will be like a minimum in between, right? And this is going to be so-called E ionization energy. And the corresponding distance is going to be the molecular separation. So experimentally, bond energy of H2 plus, that means the energy you need to pay to break H2 plus to one ionized hydrogen atom and one usual hydrogen atom is equal to 2.65 eV. And so this is our E star. And the bond length, let me call this R star, is equal to 0.106 nanometers. Any questions? Maybe we can take a break, and when you come back, we can think about hydrogen molecules without any ionization, like 2 ions but 2 electrons.